Yeah, I'm serious. Here's one of them. E to the x minus e to the negative x over 2. The other one? E to the x plus e to the negative x over 2. Should I put a y equal to in front of them? Okay. Now, does anyone want to see what these graphs look like? See, these are the hyperbolic functions, right there. But we're going to call them something else because of the behavior. Now, if you want to see the graphs, everyone, they're shown on page 258. This guy kind of went like this. This guy kind of goes like this. One of them's even, one of them's odd. Can you tell?
Mm-hmm.
If you know even and odd functions. Even functions symmetrical with respect to the y-axis.
Mm-hmm.
Odd functions are symmetrical with respect to the origin.
Origin, yep.
Which one's the odd function?
Left.
Yeah, you're odd. You're an even function. But mathematicians got an interesting feel for these. There's an application with these, so we'll do an application problem. These types of functions you can see in actual real life, real world problem. But they looked at the derivatives and they noticed things happen. So can we take the derivative of one of these?
Yeah.
I say, and then we're going to call it something else. Sound cool? Sound good? Let's differentiate that one. Let's find the derivative of y with respect to x to this guy.
So low d
And something funny happens. And we'll do, oh, I heard it. We're going to do what rule?
low d high minus
Will
high.
that work, Owen? Quotient rule
No.
for this one? You can if you want. But what's another way you can do it?
Just take the derivative of each one.
All right. Hey, first of all, he says, can I erase that image? I'll put it up here. Like this. I want to get the derivative of this so you can see what mathematicians kind of discovered themselves. Then take the derivative. He said quotient rule. Absolutely, that's a great idea and it can work, right? But I was wondering, is there another way to do the derivative? Because the denominator doesn't have a variable, it just has a what?
Constant.
Constant, yeah.
So I might look at this problem as just what?
1/2.
Maybe a half in front. But it's up to you. Please note, you could do quotient rule. Right? You could do quotient rule, but can we look at it like that? Alright, so let's differentiate this. Alright, that's what. Alright, now. Y prime. That means constant what? You stay. We don't need a product rule here. Let's start with that guy.
Each bed.
What's your VDX?
E to
Yeah! Have a great?
Mm-hmm.
Alright, we got a chain rule here. Be careful, because that's not e to the x. That's e to the negative x.
So that's e to the power negative x times minus 1.
Yeah, you're good at these. I saw that great. Like if it's e to the 2x, the derivative is e to the 2x times a 2, right? Times that chain. Or e to the 3x, e to the 3x times a 3. Well, derivative of this will be e to the negative x times a negative 1. So, alright, e to the negative x times a negative 1. Well, what's a negative times a negative?
Positive.
confidence.
And something interesting they realized. You go, what is it? Well, they like these functions, these hyperbolic functions, and they use them. But that derivative is actually that one.
Oh, yeah.
They go, oh my gosh. They like both of these functions, right? Already playing around with these functions. You know what's interesting? The derivative of this function is actually what? That one. And it's funny, everyone, we won't do it now, but if you differentiate that function, you know what? You would get
Bad.
that one.
Well, yeah.
You might be able to see it. You derivative of that one's gonna be that one. So they're like, this is funny, this is kind of like the trig functions. That's what they realized. Because what's derivative of sine?
Cosine.
Cosine, right? Sine of x, cosine of x. So that's what they did. So they go, hey, you know what we'll do? Let's call this something. We're going to call this. Well, you can't call it sine of x. So they'll just put an H right after SIN. So everyone, SIN, put the letter what? H, and then parentheses X. We're gonna call that, now what do you wanna call it? Does this sound good? Hyperbolic sine? Hyperbolic sine of X, will that work? But you might come up with your own phrases. You know what I mean? When you're reading it to yourself, you might go sine H, or sin, I don't know. You might do it. Now, so guess what they're gonna call this guy?
Cosh.
Quash. When we went around the entire math department a year ago, and every colleague, do you call it kosh or kosh? No lie, I got like 15 answers of kosh, and I got 15 answers of kosh. So I don't care what you call that thing.
Kosher.
You know, it's hyperbolic cosine, right? Hyperbolic cosine. Now, this is the funniest thing. Students sometimes, when they're hitting these on their calculators, you can go to your catalog, you'll see these. Do you know where catalog is on your calculator? You want to get it real quick? Hit second zero. Scroll down to either C or S. You'll see a COSH somewhere. You'll see sine H. It's in there. But they're representing what? These two. These are the functions they're talking about. They just named it something else. Isn't that cool? Did you see it in the list?
Yeah.
Is cosh in there?
Cosh, -1.
Oh, that would be inverse cosh. That'd be the inverse cosine. Right?
Yeah.
Hey, I'll be honest with you. You might say, hey, we're going to get the inverse cosines in here. No, remember I said the time allotted for this section? They just wanted us to get a what? You know, just a little taste of this stuff, because you will see a couple of these like maybe in a DE course. But I think we could say this. What's the derivative of hyperbolic sine equal to?
Cosh of X.
Well, here's the way I can write it. Derivative, right? Differentiate with respect to x, you get the cosh, right? Now, don't think this is exactly like trig, because check this out. It's not precisely trig, because the derivative of cosh isn't negative hyperbolic sine, it's just what? It's just hyperbolic sine. Isn't that cool? Isn't that cool? Now there's a bunch of these listed, and if you want to go to page 259, I'm going to put another one down. I want to see if y'all can predict it. What do you think this would be? Now I'm writing something, but I need you to figure out how I came up with this. I haven't drawn that on the board yet, but how do mathematicians refer to this? Isn't that the ratio of what?
Sine over
Oh,
cosine.
you're good. Sine over cosine is tangent of x, right?
Yeah.
And so that's why I remember Josephine were talking the other class a few days ago. It was about the trig identities. And I go, all right, for now, make sure we at least know that one. So this function right here, they're saying take the ratio of those two right there. This divided by that. Which you could do, everyone. You know how to divide fractions, right? Well, guess what that derivative is? Secant squared. And everyone, do they put the 2 after the h? I think they do. Yeah, they like to put that squared like right after there. Like that. I know if you're like, well, for our test, since we hit this section kind of light, you go, which ones would I have to know? It's these two. I bet you have no problem remembering, huh?
So then secant x will be what? Like secant x, secant x tan x.
Oh my gosh, he just nailed it. He just nailed it. Ah, but I noticed something, because I didn't even look at that one. It's actually negative.
Negative.
I know. I won't write them on the board. It's funny, because Art, it's like, how much do they want us to do with this section? They want to make sure the students got a feel for it. Definitely know about these two, but there's more. And he was just asking, is the derivative of hyperbolic secant equal, the derivative of that, is it hyperbolic secant times hyperbolic tangent? It is, but it's negative. Do you see it? You see, he sees it. So it's close though. What they noticed was there's a close relationship starting with these two functions and trigonometry, right? But this is hysterical. When students start doing this, sometimes this will happen to you. You might think you got to be like in radian mode. To do this, you don't have to be in radian mode to hit these on your calculator. Right? Do you see any trig in there? No, they just called them this because of the relationship of how it was. It was almost like identical in terms of derivatives with the trig functions. So you don't have to be in radian mode. Just always remember, what were these functions? There's no trig in there. These are exponentials, right? So don't think, like, you can be in any mode when you do these on your calculator. But you bet, everyone, if you want to find what's going on with that function at x equal to 17, you could hit that on your calculator and put what number it is?
17.
17? I think it's quicker. I think it's easier to type in than this, right? If you gotta find the value of this at x equal to 2, you could just hit cosh of what?
2.
2.
We could go to the catalog thing and just.
That's what you do. You just go, it's probably in another menu on your catalog, but you go to the catalog, and you hit that, and then you put what number there?
17.
Yeah, so hey, I'm curious, what's cosh of 17?
3.524.
Is that what it is? Check it out, Kayla, 3.5 what?
3.52549.348.
Yeah?
I didn't get that one.
Oh, what'd you get?
Just really.
Oh wait,
That's not it, Amber?
I don't think so. I
It's
did
a
the
very
negative
big
one.
number.
Did you hit coast by accident?
I think no, I did.
I apologize.
I did a negative one.
Alright, we'll edit that out.
Like 12 million. Yeah, it's 12 million.
12 million?
Yes.
Yeah.
Give me all the numbers.
12 million? Wow.
120774776.
120774. And remember the graph was doing what? It was like this, so when we got only out to 17, this sucker was what? It was high, huh? It was high. Cool. Hey, these types of functions, have you ever modeled anything that you're aware of? Go to page, if you got your book, go to page 259, and you're all gonna recognize and structure, then we're gonna find out if anybody in this class has been up in it.
You can go up.
Who's been in the Gateway Arc in St. Louis? I'm curious. The actual equation that represents that what? Which one of these two does it behave like? It's like the cosh. And there's an
yeah.
equation for it. You can look it up on the internet if you want.
But inverse, right? So that should be
No,
negative.
the author wrote it. So when you look on page 259, no one in here's been there? Usually I get like one student who's been there. You're like me. You stay in Maryland. This morning in stats, we did Old Faithful, you know, at Yellowstone Park. So who's been at Yellowstone Park? No one's been there either. Well, these places are far away from here. Usually I get like one student who traveled with their parents and been there. But hey, everyone, if you wanted to see the equation for the Gateway Arch, would you go to page 263 and look at that equation? Does anybody want me to write it on the board? Everyone? You want to know what it's designed? You want to see the equation?
Number
All right,
48.
there it is. You could have saw this on Wikipedia. So it didn't use this in the equation, but it has one of these guys, and here it is. Gateway Arch. And this is in St. Louis. But the elevator just kind of goes up like this as it goes around. So you get a nice view of everywhere. But it's probably like, you know, trying to get in the monument. Sometimes the monument's not open, is it? Sometimes they have to do what? Yeah, they got to do a little maintenance and stuff like that. Remember that earthquake a
Mm-hmm.
few years ago? That did some damage to the monument. Do you know that?
But that's in DC, right?
Yeah. And that was the earthquake
It was like
that was in Virginia,
Uh-huh.
damaged that monument.
In centralized
Isn't
Missouri?
that amazing? Yeah.
Wow.
And you got to ask Professor Major about that.
Oh.
Would you email her tonight?
I had lost it. I
If
don't
you
know.
all right.
Yeah.
PG Mazer at AACC. Just say I mentioned that because she was the one who informed me. She went down. She goes, "Do you know?" She went down there. She goes, "Yeah, I think that somehow got damaged. Like it just, I don't know, damaged, but it shifted. Like it somehow the whole monument and everything shifted a little bit." All right, here we go. Y equal 211.49 minus 20.96. Boy, they're never neat numbers, are they? Gosh. So tell me about this then. 0.03291765x. Okay, 0.03291765 times all that. Right? That's what they're saying, right? But how does it look? It's kind of what? It's like that. But you saw the cosine graph, didn't it go like this? But what's in front of that?
Negative.
So that's cool. Now, we're gonna do our own application problem. So I'm gonna do,
So do they use this kind of cost function to make bridges and all?
to make what?
Bridges and all this kind of stuff?
They do.
They do.
And bridges, another place, is power lines.
Gotcha.
I want to know a catenary. It's just, you ever see the power lines, how they hang?
Uh-huh.
Here's the pole, here's the pole. It's not tight, is it? It's what?
It's like kind of.
It's like right outside my house. We're just gonna let all the birds hang out on the thing. And the thing just sits right there. Yeah. I'll tell you though, a month ago, man, there's a bird. If I walked outside, the thing would attack me. I mean, it must have built a nest right near my door. But that's what he do. He'd sit up on the power line. I'd come out and go crazy, and I'd go to the mailbox, and he'd just come diving down at me. What did I do? What am I doing? He must have built like right near the house or something. He's upset I had my light on at night, grading math test or something. Turn out the light. I'm trying to sleep in the trees. I don't know. All right, so we're gonna do. This is number 51. It's on page 263. Cool. And I'm thinking of this one. And what I'm gonna change a little bit. Does that sound good?
Okay.
Put light. Because I know I put that as one of our practice problems for you to work. Alright. Here comes the power line. Y equals, they got 20, I'll use 25. 25 cosh x over 25 minus 15. All right. Now, let's only consider this on the interval